In this video, we'll go ahead and look at some special cases for second-order ODEs. Case A will be when we have equations with y missing. So let's say that we have something of the form of the second derivative of y with respect to x plus some constant a1 times the first derivative of y with respect to x equals some function of x. So this is the equivalent of saying y double prime plus the constant times y prime is equal to some function of x. In order to solve this, we're going to make a substitution. We're going to set p equal to y prime and p prime equal to y double prime. So in both of these cases, p is also a function of x. This transforms our original ODE into a first-order ODE. Which we can now solve with our first-order ODE strategies. Once you solve for p as a function of x, we'll need to substitute back p for y prime. That will give us a new first order ODE, which we can then solve for y. Our next case will include equations where the x is missing. So with this sort of scenario, and we'll do an example here in just a moment, means that we've got a differential equation with y's, y primes, y double primes, but no x's in there. So again, we're going to make a substitution. We're going to set p equal to y prime, but we're going to treat p as a function of y now. Instead of p as a function of x, as in the previous case. So that means our y double prime will look a little different. And I'm going to go through and do a quick proof to show you what you should be plugging in for y double prime. Now, if y prime is equal to p, then y double prime should be dp dx. But again, p is now a function of y, so we have to think about our chain rule. So this is actually dp dy, and then dy dx. But dy dx is y prime, and we said that was equal to p. So that means we have dp dy times p. So this is what we'll plug in for our y double prime. Once you go through and do that, again, you'll have a first order ODE. So the steps will be to solve for p as a function of y, then substitute back, to solve for y as a function of x. So let's take a look at an example for this. So in this example, 4y double prime minus 2y prime squared plus y equals 0 has a missing x. Or if you want to think about it, it could be t, whatever the appropriate variable is. So if we were to look at this ODE, this could be y double prime could be acceleration, y prime could be velocity, y could be position, and those could all be as a function of time, just as an example. So in order to go through and solve this, using our special case B, we're going to substitute y prime equal to p, and y double prime equal to p times dp dy. And again, p is a function of y in this case. So, making that substitution, we now have 4 times p times dp dy minus 2p squared plus y equals 0. Now I'm going to do a little bit of algebra to get this into a form that we recognize. We typically want the derivative to be by itself. This is now a first order equation. It's not linear, but it is first order. So first I'm going to divide everything by 4p. So now I have my derivative by itself. If I do a little bit more algebra, I can see that I can get this into the form of a Bernoulli equation. So to solve a Bernoulli equation, we again need to make another substitution. So on the right-hand side, we have p to the power of -1. So for our particular Bernoulli equation here that we're looking at, our n is equal to -1, which means that we're going to make a substitution to z, where that is going to equal to p to the 1 minus n power. In this case, that's 1 minus -1, or p squared. Then z prime will equal 1 minus -1 p to the -1 power times p prime, or in other words, 2 times p prime. And again, p prime here is dp dy, because p is a function of y. So if we go back and look at our equation that we had earlier, before we got it into the form of the Bernoulli equation, sometimes it can be easier to do your substitution back into an earlier form. So if I take a look at this first term, 4 times p times dp dy, which is essentially p prime, is basically 2 times z prime. This next term is 2 times my z, and then I still have my y. So with this new substitution, I now have what is still a first order ODE, but it's now a linear first order ODE. If I divide everything by 2 and move the y to the right hand side, it'll look like our more normal forms. So now, to go through and solve this, I'll follow my rules for the linear first order. First, I take the integral of whatever is multiplied by my z, that's just a -1, and I'm integrating with respect to y, so that gives me a -y. Next, I integrate whatever's on the right-hand side, multiplied by e to the result of my first integral, so e to the -y. Integrate that with respect to y. If you throw this into Mathematica, you'll find the solution is 1/2 e to the -y times 1 plus y, and then our constant c. So then our solution, z as a function of y, will be the exponential times the negative result of my first integral, which makes this positive y, times the result of my second integral. Which I could simplify a little bit more. My e to the y times e to the -y exponential just gives me 1. But then I still need to multiply e to the y times my constant. So that's my solution for z as a function of y. But that's not the solution to the problem. I now have to go back and reverse the various substitutions that I did. So the first one that I'll go through and do is to substitute back to p as a function of y. The substitution we used into z was z equal to p squared. So that basically means I've got p squared is equal to 1/2 1 plus y plus c e to the y. So that means p as a function of y is just equal to plus or minus the square root of all of this. Now, in order to get it into a function of the function y as a function of x, we need to substitute back. And earlier we set y prime equal to p. So that means that this p as a function of y is actually dy dx. If we think about this problem as we started earlier, where y double prime was acceleration, y prime was velocity, and y was position, that at this point I actually have the solution if I want to know how velocity goes as a function of time, or position actually is what this is showing. Since my solution right now only depends on y, it does not depend on t. So the next step, if you were trying to get a solution of position, then what we would go through and do is we would separate the variables here. So I would take everything that has y and move it over to the left-hand side, everything that has x or t, again, I keep talking about this as a mass moving and a function of time. All of those x's could be written as t's. It would be the same thing mathematically. So I would go through and do that separation. So that would give me something that looks like this. I would integrate both sides. And then as long as those integrals are doable, I would eventually get myself to a solution of y as a function of x is equal to some stuff. It turns out that this integral cannot be integrated, analytically at least. So if we actually wanted a solution to this particular problem, to know what position the object would be in at certain times, then I would need to go through and do this numerically. This is where our computational methods would come into play. And in order to do that, I would need to know some sort of initial values or boundary conditions. Basically, where is the object at a certain time? What speed does it have at that one moment? So that I could pin my solution on those physically measurable values. But that gives you an idea of the steps that you would need to go through to use this method. Now, it's quite possible that after you make that first substitution, you wouldn't have a Bernoulli equation. Maybe you would have a linear equation, first order ODE at that point, and then you wouldn't have to do that intermediate substitution step. But the main idea here is that we turn it into a first order ODE for which we have other methods of solving it. Then we just need to go back through and integrate one last time to find the final solution. So our next special case, C, is going to be equations that have the form y double prime plus some function of y equals 0. And this is basically a special case of B, the method we just looked at. So if you see something that has this particular form, what you want to go through and do first is multiply both sides by y prime. Now if I go through and do this, I can basically factor, or excuse me, if I go through and do this, then I can multiply next the entire thing by dt, and so if I go through and look at this, and I'll rewrite this one last time actually, I can write this first term here as y prime times dy prime dt. The second one is the equivalent of the y double prime. And I can write my y prime here as dy dt. All of that equals 0. And so if I'm multiplying this entire thing by dt, then that's going to change this a little bit so that my first term now becomes y prime dy prime, because those two dt's cancel. And the next one will be my function of y times dy, because those two dt terms cancel. And all of that's going to be equal to 0, because dt times 0 is still going to be 0. So if I go through and look at this now I've got different terms. They are separated. So here I only have y primes. Here I only have y's. I can integrate each of these individually. So I can do the integral of y prime dy prime plus the integral of f of y dy times the integral of 0 times dt, which is essentially just a constant. That constant could be 0, but it could be 5 or 2.34 or any number, as long as it is a constant. For my first term here, if I go through and do this integral, that's a fairly simple one, so that's going to give me 1/2 y prime quantity squared But then I'm still left with this one that I can't go through and evaluate unless I know what that function f happens to be. So for your particular ODE, you would know what that function is, and you could go through and do that integral. So let's take a look at an example for this one as well. So an example in this case could be acceleration, or excuse me, could be involving Newton's laws here. So let's say that we've got mass times acceleration is equal to some force that's position dependent. So again, our mass here is just the second derivative of position with respect to time, and that's equal to whatever this force happens to be. If I can maneuver this around into the form that we were given when we first introduced this method, I'll have m x double prime. I'll move my function of x over to this side, that equals 0. And now I need to divide everything by mass. Okay, so this is the correct form that we want to go through and use. And the reason why we want to make sure we get it in the correct form first is because I need to know what the part that I'm going to integrate is, which in this case is right here. So again, to solve this, I multiply everything by the first derivative. And then I can go through, multiply everything by dt, and integrate each of my pieces. So the first term will always integrate to the 1/2 first derivative squared. The second term is the one that I need to focus on. The 1 over m is a constant, so I can pull that out. So I would be integrating whatever this force that's dependent on position happens to be. And then again, that's going to equal a constant. Now I'm going to multiply everything through, multiply the mass through again, so we can take a look at what we've got here. Since we started with an actual physical problem, we should be able to look at the pieces of this and relate them to physical quantities. So this first term here, 1/2 m, x prime is velocity, so this is 1/2 mv squared. That is our kinetic energy. This part here, the integral of the force that depends on position as a function of that position, is work. And if you remember back from your introductory physics classes, the negative of work is your potential energy, which means that what I've just derived here is kinetic energy plus potential energy equals your total mechanical energy. So we just derived energy conservation from Newton's laws, essentially. So again, if you were going through and doing this problem in order to get to a final solution, you would need to know what that function f of x is, do that integral. Then you've got yourself a first order ODE, which you would then need to go through and integrate again to get to your final solution. So this example isn't a full example of how to go through all the steps, but we did that in the last one. And I'm confident that you all can do that on your own as well. Our next special case, D, are known as the Euler-Cauchy equations. And they also have a very specific form to them. So if you see something of the form a constant times x squared times your second derivative plus a constant times x times the first derivative plus a third constant times the function equal to some function of x, then that is known as an Euler-Cauchy equation. So in order to go through and solve this, we've got two different methods that might work, and they're variations of each other that we'll go through and take a look at. So if that f of x on the right-hand side happens to be 0, then we're going to try a substitution of x equal to e to the z. And I'm going to go through and do the proof for this so that you can see how this works. But when you're going through and doing this with homeworks and problems and whatnot, you'll be able to jump to the final sort of solution here. So again, I'm going to go through and do the proof, but you'll be able to jump to the end result. I just want to make sure you realize why this can work. So if we go through and look, if this is a substitution we're doing, then dx dz is also going to be e to the z, as is the second derivative of x with respect to z. That's partly why we're using the exponentials. But in order to go through and do this substitution, we need to know how y relates to z. So we need dy dz. Again, we can go through and use our chain rule. That's the same thing as dy dx times dx dz. dy dx is still just dy dx, but we know that dx dz is essentially just x again. We'll do the same thing for the second derivative. So the second derivative is just d dz of the first, which we've already figured out, is x times dy dx. And it doesn't matter what order I write these two in from the first line to the second line here. So I need to go through and do my product rule to multiply this derivative through. So I will have the derivative of the first one, which is dx dz, times the second term, plus the first term times the derivative of the second one. So again, dx dz is just x. So I have x times dy dx. And then I have x times the derivative of y with respect to z, and then x. But it actually doesn't matter which way I take those. That's the same thing as saying the derivative of y with respect to x and then z. There's nothing wrong with saying that. Which means I can pull out that dx derivative. And this one's a little easier for us to go through and take a look at. We've already written out what dy dz is, so I'll plug that in from above. And I can switch the order of these. So I'm going to switch these two. So now I have dx dz times the second derivative of y with respect to x. And I'm getting closer to something that I can actually use here. Dx dz we know is just x, so now I have x squared times the second derivative of y with respect to x. And again, this right here is just dy dz. So if I go through and look at all of this, I can rewrite it, solving for my third term here. So far what this has allowed me to do is, for my substitution, setting x equal e to the z, I figured out what each of my derivatives can be, and I can substitute them back in. So again, our starting equation looked like this. And with my substitution, I can go through and substitute in for each of these pieces. This x squared, second derivative of y with respect to x squared, is exactly what I just solved for up above. So I can plug that in for this. The x times dy dx is just dy dz, and then my y and my function will stay the same, except for this is now going to be a function of e to the z, because again, we need to substitute in for the x. So, going through, plugging these in, and maneuvering some things around, because I'll have two terms that'll have dy dz in them, each with different constants. The final form, the one that you'll be able to jump directly to if you have this particular case, looks like this. So this is a linear second order equation, ODE, with constant coefficients. So now you'll be able to go through and solve that using our previous methods, because all you have to do is worry about those constants and what they mean. So earlier, so this is true for any ODE of the form. I didn't actually specify what this function over here needed to be. So now I'll actually go through and take a look at what are the ways that we can try and solve this, depending on what that function happens to be. So if our f of x is equal to 0, we're going to try a solution that looks like x to the k power. So that means that our y prime will be k times x to the k minus 1 power, and our y double prime, k times k minus 1 x to the k minus 2 power. So we're actually going to plug this into the original ODE, not the new one that we just had. That would be if you've got a non-zero function there. So I've plugged that in, and you can see that things will simplify a little bit. This x squared times the x to the k minus 2 we'll turn that into x to the k. Similarly, this x multiplied by the x to the k minus 1 will also give me x to the k. Which means that I can divide everything by x to the k. And so now, all I'm left with is an algebra problem where I need to solve for k. Now, if you go through and solve for k, and it comes out that it's complex or it has equal roots, this method will work pretty well. Otherwise, you're actually better off going up above to the one that we went through and solved. So to summarize this one, because I think I misspoke a little earlier, the Euler-Cauchy equations have this general form. If that f of x is 0, you're going to try substituting y equal to x to the k power. And this should work as long as k isn't complex or when you go through and solve it, it's got equal roots. So that basically means when you go through and solve this, you're going to end up with two possible options for k. So your solution would then be a linear combination of those two. So if we went through and did an example and found k to be equal to 1 or -3, then our solution would be a linear combination of those two. Y would be equal to some constant times x to the first power plus another constant times x to the second k power. So that would be our general solution. And so this is why if you have equal roots, if those two numbers were the same, if k was just equal to 2 and 2, those are the only top possible ones that worked, then this, you can see that this solution is not going to end up working. You really only have one term there. So if f of x is not equal to 0, which is the part where I think I misspoke earlier, then you're going to make the substitution x to e to the z. That'll switch your ODE to this form. You'll solve that second order linear equation with constant coefficients for y as a function of z. Then you'll need to substitute back to get y as a function of x. So So the last special case we're going to go through and look at, special case E, is called reduction of order. So let's say we have an ODE with this general form. If you have something multiplied by your y double prime, you can go ahead and divide it through, and you'll get this form. So this method assumes that you know at least one solution. We'll call that solution u as a function of x. And we'll go through an example on this in just a moment. But oftentimes you can go ahead and look at that ODE and figure out a very simple solution. Maybe the solution is just y equals x, which is what we'll see for our first one. So this method will work if you can go through and very quickly figure out at least one solution by inspection. Is usually the easiest way to go through and do it. So if we know at least one solution that works, then what we're going to do is we're going to substitute y is equal to u times v. U is the solution we know. V is some unknown thing. So we're going to need to solve for what v happens to be. And v should also be a function of x. And that will give us a second solution. So let's take a look at an example with some real numbers here. So x to the third power times y double prime plus x times y prime minus y equals 0. Now I don't actually have to go through and divide by the x cubed to put it into the form that I've shown up above in order to go through and use this method. But because I basically can go through and look at it and see that it does satisfy that. If I go through and divide by that x cubed, I could see that yes, that fits that particular method. But since it's not actually important to solve the ODE, I'm not going to go through and do it right now. I can plug in just as things stand right now. So going through and looking at this, let's say that I could tell by an inspection that I know that x is a solution. And to verify that real quick, u prime would then be 1 if I take that derivative once, and u double prime would be 0. So that basically means that I'm going through and looking at this and saying 0 plus x minus x equals 0. So yes, that is clearly a solution. And that's what I mean by sometimes you can inspect to find a very simple one easily. So since I know that is a solution, I'm going to try y is equal to my solution, x, times this unknown function v that I'm going to try and solve for. And I'm going to need to plug this and the derivatives into my ODE. So my derivatives, y prime, x times the derivative of v plus v. So my first one times the derivative of the second plus the derivative of my first times my second. Repeat again to get y double prime, which I can simplify a little bit.